Okay, so today we're going to look at equations lines again, just like we did yesterday. But yesterday was in 2 space, so now we're going to look in 3 space. And we're going to see that the lots of connections between 2 space and 3 space. So of course 3 space, remember, is 3-dimensional. So we add the extra dimension. We don't just have a length and width, we have a depth, or an x and a y, we have a z. And the advantage of this types of modeling I talked about yesterday is that it's easy to go to 3 space. If we looked at our grade 9 models of lines, equations of lines, it wasn't easy to get to 3 dimensions. So, but this is just a matter of adding the z, but you're going to see a lot of the similar stuff that we did yesterday on day 1 will be happen right here. And it starts with something very familiar, the direction vector. So in this case, you'll notice that this vector goes from A to B. So to find the direction vector, of course, we do b minus a. And so now it's 5 minus minus 2 is 7. 4 minus minus 7 is 11. And 6 minus 3 is 3. And so the direction vector 7, 11, 3 is the exact same direction vector, is the direction vector of this line. And remember, any scalar multiple of this direction vector would also describe the direction of this line. So I could go the opposite direction and go -7, -11, -3. That would also be a direction vector. Or multiplied by 2, 14, 22, 6 would also be a direction vector. All of these describe the direction of this particular vector. Now in 3 space, you'll notice that we have similar types of equations of lines. So the ones that we had yesterday can be expanded to look in 3 dimensions, or 3 space. So if you wanted, you could go back and look at the general, the vector, symmetric, and all the different types and see how they're similar as we go through this, but that's up to you. The general equation then it looks exactly like yesterday's general equation, but introduces the z. So we're going to go from x, y, z this time. So any point in 3 space can be found by taking any given point. So again, let's just pick one from here. I'll choose B again because there's no negatives in it. So I'll just choose this one, the 5, 4, 7, or 5, 4, 6, excuse me, plus a scalar multiple of the direction vector. And we just discovered the direction vector was 7, 11, 3. And so just like yesterday, we can describe any point on the line by taking any given point and adding a scalar multiple of the direction vector. This is the best equation of the line to visualize what's going on. So remember, like I showed you yesterday, you take the point and you add scalar multiples in either direction of the point, scalar multiples of the direction vector of on any spot in the line. You'll get any other point on that line. You can take the big ones that get you in the positive direction, the little ones, and the little ones in the negative and the positive direction. Now, from the general equation, we can go to the vector equation. If you recall from yesterday, the vector equation just brings the point over. So we're going to subtract 5, so x minus 5, y minus 4, z minus 6 equals k 7, 11, 3. It's called the vector equation because it isolates the vector, the direction vector. You can see the direction vector there. And the coordinate is all within here and opposite to what you think. So just like yesterday, when you see x minus 5, it's referring to 0.5 at 4 and 6. Next on our list from yesterday was the symmetric equation. Well, we're going to come up with the symmetric equation here. And if you recall from yesterday, the symmetric equation came from dividing the direction numbers of the direction vector. So we've got this x minus 5, and we're dividing by the x part of the direction vector. The y minus 4 gets divided by the y part of the direction vector. And all we're doing is adding a z component now. Z minus 6 over 3. And just like yesterday, these numbers along here are called the direction numbers. Now, if you are following along from yesterday, the next one we looked at was the general equation, or the scalar, or sorry, not the general equation, the scalar equation, or the standard form of the equation. That came from cross multiplying. Well, now that we have three situations, we can't do that. So there is no scalar equation for a line in 3 space. We can't cross multiply here because we've got three things here, so it doesn't make sense. I'm going to stress that there's no scalar equation for a line. You actually will see next unit where that comes into play. But for right now, scalar equation, or the standard form, only works in 2 space like it did in grade 9. Doesn't work in 3 space. So we don't have a scalar equation, but we do have a parametric equation. And if you recall, the parametric equation describes all of the x's, the y's, and the z's. And it comes really from the general equation. It says that x is equal to 5 plus the scalar multiple of the x component. So x equals 5 plus 7k. The other two are going to come from the same spot. Y is equal to 4 plus 11k, and z will be equal to 6 plus 3k. So good news, that looks just like the parametric equations in 2 space, but introduces the z component to make it 3 space.